Welcome to the Explainer. Let's just dive right into this. Today, we're unpacking the sheer, mind-bending astrophysics of Caldwell 15, affectionately known to astronomers as the Stoplight Nebula. We're looking at a stunningly complex cosmic structure here, and we're going to explore exactly how it works, using some of the latest data to decode its secrets.
6,000 darsa. That massive number is the distance in light years we're traveling today. We're heading deep into the Cygnus constellation to reach our subject. To put that into perspective for you, the light we're seeing from Caldwell 15 right now, it left that nebula thousands of years ago. It's literally a deep space time capsule, and it has a whole lot to teach us about the life and especially the death of stars.
To keep us from getting lost in the deep space data, here's our roadmap. We'll start by meeting the Stoplight Nebula, break down the anatomy of a gas shell, and then plunge right into the heart of the nebula. After that, we'll look at the rhythms of stellar rotation, decode those chaotic cosmic winds, and finally, look at what this all means for our own solar future. Basically, it's a macro to micro journey, starting wide and zooming all the way down to a violently churning central star.
Section 1. Meet the Stoplight Nebula. Let's start wide and establish exactly what it is we're looking at up there in the night sky.
Before we go any further, let's set our baseline. Caldwell 15 is a planetary nebula. Now, despite the name, I gotta clarify, this has absolutely nothing to do with planets. It's a bit of a historical misnomer. A planetary nebula actually represents the magnificent death throes of a star. Specifically, it's the ejected stellar material from a dying low to intermediate mass star, which forms this glowing massive shell of ionized gas. It is the spectacular glowing finale of a star's life.
And the nested architecture of Caldwell 15, which is also cataloged as NGC 6826, is just striking. It's not just some random fuzzy cloud of gas, you know? It's a highly structured series of layers. Look at that bright inner elliptical rim, the axiosymmetrical outer shell, and those embedded dense knots, which are called fast low-ionization emission regions, or FLIRs for short. Add in a faint massive spherical halo extending way out into the interstellar medium, and it is quite literally a brilliant, glowing cosmic onion.
Moving on to Section 2. Anatomy of a gas shell. We're going to decode those layers by peeling back the glowing nebula to really understand its underlying mechanics.
The physical structure of Caldwell 15 operates a lot like a giant wind-blown bubble. This is driven by what's called the interacting stellar wind model, and it works like this. Extremely fast, tenuous winds blowing off the hot stellar core essentially crash into the older, slower, and denser winds that the star ejected much earlier in its life. This brutal collision creates a central cavity filled with shocked gas that's burning at tens of millions of degrees Kelvin, that's surrounded by a dense, swept-up shell where the actual collision happens, all wrapped up in a massive outer envelope.
When we map out the actual mass and density profiles across these regions, we get a mathematical snapshot of the expanding halo. It shows exactly how the mass accumulates as we move outward from that central star. The sharp drop-offs and peaks in the data are super important because they tell astrophysicists exactly where those dense shells of crashed stellar wind actually reside. It gives us an incredibly accurate physical map of the nebula's anatomy.
Which brings us to Section 3, Heart of the Nebula. We've taken in the wide-angle view, so now let's plunge directly into the absolute chaos happening right at the center.
Because the crucial point here is, what on Earth, or rather what in space, is generating these massive, violent winds? I mean, what kind of engine could blow a structured bubble thousands of times larger than our entire solar system?
Well, the engine in this case is a ZZ Lep central star. This is a specific, highly variable class of central stars found inside planetary nebulae. This incredibly hot core doesn't just sit there shining steadily. Far from it. Its light and wind output fluctuate wildly and completely unpredictably. It's a chaotic, violently churning core that's constantly changing its behavior over a matter of mere hours.
Section 4. Rhythms of stellar rotation. Finding the rhythm of this star is absolutely key to solving the mystery of its extreme variability. And to do that, astrophysicists turn to long-term photometry from the Kepler spacecraft.
Think of this data as a literal heart monitor for the star. By analyzing amplitude and time Fourier spectra, which basically track the star's pulse over time, scientists were trying to find a steady, predictable rhythm hidden deep within the sheer noise of the star's chaotic energy output.
And what the data reveals is this fascinating duality. On one side, we have a steady 1.24-day rotational heartbeat. The star is spinning, right? And as it spins, we see a predictable modulation in its light, almost like the beam of a lighthouse. But locked in a fierce battle with that steady spin are completely chaotic, incoherent light variations that happen over just hours. It's exactly like a steady drum beat being totally drowned out by a completely erratic, unpredictable guitar solo.
That takes us to Section 5, Chaotic Cosmic Winds. Let's decode those frantic hourly variations, because what we're really looking at here is some severe stellar weather.
Data from the DIFFUSE satellite reveals the presence of what scientists call discrete absorption components, or DACs. If you notice the dark bands migrating upwards in the spectrum, well, those represent massive blueward migrating storms in the star's wind. We're talking about literal clumps of material accelerating away from the star at hundreds of kilometers per second. It is the visual fingerprint of a wildly unstable stellar outflow caught in real time.
You can really think of this as severe weather on a stellar scale, and it forms in 3 distinct steps, creating what are known as co-rotating interaction regions. Step 1. Intensity variations, kind of like massive sunspots, erupt on the star's glowing surface. Step 2. These spots locally modify the velocity of the outward-flowing stellar wind. In Step 3, as the star rapidly rotates, the fast winds violently collide with the slower winds ahead of them, and that creates massive spiral density fluctuations. Just imagine a spinning sprinkler head shooting out water at different speeds, creating a spiral traffic jam that just plows outward into the nebula.
Section 6. Decoding our solar future. Now let's bring this distant, chaotic phenomenon right back home to our own cosmic neighborhood, to decode our own destiny.
As the research states, understanding the mass loss and fast winds of central stars is critical for decoding stellar evolution. Studying Caldwell 15 isn't just about cataloging some pretty distant nebula. No, it's about looking into a cosmic mirror. Because the Stoplight Nebula was actually formed by an intermediate mass star, it serves as a direct preview of the evolution of all stars in this class. And yes, that emphatically includes our very own Sun.
So as we unpack the beautiful but incredibly violent mechanics of the Stoplight Nebula, it leaves us with a truly provocative thought about our ultimate cosmic destiny. Billions of years from now, when our own sun reaches its death throes, will it generate the exact same violent, spiraling winds to paint the cosmos with our solar system's remains? It's a humbling thought to end on, but one that really underscores just how connected we are to the broader universe. Thank you so much for joining me on this explainer, and I encourage you to keep looking up and stay curious.